Good evening, and welcome to the current installment of the SLAC Public Lectures. I'm very glad to see you all here tonight. Today we're going to talk about a hypothetical particle called the axion. Many of you may have gotten the impression from previous public lectures that the dark matter of the universe is some heavy, invisible particle. And we wanted to break that impression to a certain extent by telling you about another candidate which is very different, which could make up the dark matter. And to do this, we're very lucky to have tonight as our speaker Hendrik Vogel, who's a postdoctoral fellow in the SLAC Theoretical Physics Group. Hendrik got his PhD in Munich at the Max Planck Institute that Heisenberg founded. He wrote his thesis on the effect of neutrinos and other invisible particles on stars, and then he came here to study more kinds of invisible particles. And so today he'll tell you about the axion, proverbially the ghost riders in the sky. So, Hendrik, thank you very much.
Thank you very much for the introduction, Michael, and thanks to everyone in the audience for being here. I'm very excited to tell you about the axion today. And as Michael said, the axion is a hypothetical particle, but if we discovered it, it might mean that we find a new way how to understand fundamental physics. It might solve the problem of dark matter, and it can also lead to innovation in everyday technology. Most importantly, however, if the axion exists, it might mean that we are basically surrounded by ghosts. But before I continue that story, let me start with a picture of the night sky. So this is similar to what you would see if you went outside in an hour from now. And what you can identify here is a couple of stars. You see Orion's belt. But if you take a step back, then you'll see that most of this picture is actually black. Most of this picture is actually the space that's in between the stars. And if you're like me, then in school you were basically told that this space is empty, that there's nothing inside there. But I want to take a closer look at that. Is that actually true? And if there is something, what can it tell us about our universe, about how it came to be? This is a picture which was taken with a much better camera by the European Southern Observatory. And this is a 360-degree panoramic view of the sky as you see it from Earth. So here, this is the Milky Way. This is the disk of our galaxy. And if you could look on top of our galaxy, then it probably looks something like this. So here in the middle, you have the galactic center. This is where a supermassive black hole resides and attracts all the stars that circle around it. And these stars, they form this spiral pattern. Our sun, our solar system, is here. So that means that if we look towards the galactic center, then in this picture, that will be a slice like this. If we turn by 90 degrees, that would correspond to a slice which looks like this. And we can look away from the galactic center, and then they would correspond to this. Of course, you can also look above or below the disk, and that would correspond to these regions here. Okay, so what do we see here? So first of all, you see these light dots again. So there are lots of stars in this picture. However, you also see this kind of structure here, which seems to obscure something behind it. And these are dust clouds. So this is similar to what you might find if you vacuum your living room, but now this flies in space. And this substance, this dust, is really good at absorbing light. So if there are stars behind it, we are not able to see them. So luckily, this visible light is not the only thing that we can use to look at the sky. So visible light with a certain frequency is here. You can go to longer wavelengths in this direction. So for example, there's radio frequencies. So this is what you might know from your car radio. This is what it uses to play music. There's microwave radiation, which has a slightly shorter wavelength, and this is named, or this tool you know from your kitchen is named after this. There's infrared radiation, and that is the radiation that the body emits, which has a certain kind of temperature. At room temperature emits this heat radiation, infrared radiation. So if you look at a person in the infrared, then you can see where this person is rather hot and where he's rather cold. On the other side of the visible spectrum, there's UV radiation. This is what gives you sunburns if you spend too much time out in the sun. If you've broken a bone, then you might have seen pictures like this, which are taken in the X-ray, which is at even higher energies, shorter wavelength. And the most energetic electromagnetic radiation that we know, that is gamma rays. And those are usually produced in, for example, black holes, so some astrophysical objects. And this black hole here, that's a blazar. It accretes matter and converts that matter into energy, which is then emitted in terms of gamma rays. Okay, let us see what happens if we look in the radio. And for this, you cannot use just a simple camera. You need something much bigger. For example, something like this. This is the dish antenna, very close by. And with this, a picture of the sky might look like this. So again, you see the galactic disk here in the middle. Here would be galactic center. And the red radiation here means that there's lots of radiation, lots of photons, very intense radiation is coming from that region. If you look above the disk, then in these blue areas, there's very weak radiation coming. Okay, so there seems to be some substance, a rather diffuse substance, which emits this. Now, luckily, at this particular frequency here, we have an understanding of what this means. What emits this kind of radiation is hydrogen. So to remind you, hydrogen, that is a proton and an electron. And protons and electrons, they have a property called spin. Spin is similar to just a magnet. And similarly, these two either want to repulse each other or they want to attract each other, depending if they are aligned or anti-aligned. So what this hydrogen here wants to do, it wants to, because these two repulse each other, it wants to spin this one around to go into this state. So this is similar to magnets. If you let go of them, one wants to turn around and attract itself to the other one. Now when it does it, it gains some energy, and this energy has to be radiated off with a wave packet, or what we call a photon, so some electromagnetic radiation. And this photon here has exactly this frequency, is 1420 megahertz. So this picture actually shows you where there is lots of hydrogen in space in our galaxy. So this means there's lots of hydrogen here flying around in our galaxy. How much exactly? Well, let's assume you could go to your supermarket and buy a gallon of space. Then it turns out you would find roughly 4,000 of these hydrogen atoms inside your gallon of space. So it's not empty. There's something inside there. But it's not that much either. If you compare it to air, for example, air has this times more atoms per gallon. So, okay, close to empty. But we only looked at the radio right now. Let's see what happens if we, for example, look in the microwave. In the microwave, the picture looks completely different from before. You see some structure here in the middle, but apart from that, the sky seems surprisingly uniform. So in whatever direction you look into, there seems to be the same intensity coming from everywhere. It's as if there's some object surrounding us which emits this very particular intensity of microwave radiation. And from this intensity, you can infer that the temperature of this object is roughly 2.7 Kelvin. That means minus 455 Fahrenheit. So this is very, very close to the absolute zero. It's a very cold object that's surrounding us there. Now, the discovery of this radiation was even surprising to the discoverers, Arno Penzias and Robert Wilson. They set out with this kind of machine here. They tried to measure some radiation coming off from some satellites. So they had to have a really sensitive measurement to actually pick up that radiation. So what they had to do, they had to calibrate their instrument here really well, really finely. They really had to understand it. And then they set out, they did some test measurements, and they saw some mysterious noise coming from every direction. Okay, they didn't understand that, so they went back. They recalibrated everything. They found some pigeon droppings inside the camera, which they had to clean up. But this mysterious noise remained. Now, luckily, not far away from them, a couple of miles in Princeton, there were a couple of theorists thinking about this kind of radiation, that it should actually exist. And the reason for this is the creation of the universe, the Big Bang. The Big Bang that happened 13.5 billion years ago should have emitted some photons. There should be some afterglow to this event. And these photons were created. They traveled through time and space for 13.5 billion years for us to be detected today. So that means that this picture is not just some radiation. This is actually a picture of the early universe, of how it was created. So this object that's surrounding us with this 2.7 Kelvin, that's actually the Big Bang. That's the beginning of the universe. So that means the temperature of the universe today, that is really this 2.7 Kelvin. So really, really cold. Okay, coming back to a gallon of space, that means that there are a couple of photons flying around as well. And you can infer from this temperature that there are 2 million of these in your gallon of space. Now, these are not ordinary photons. These are really photons coming from the beginning of time, from the Big Bang. Now, it turns out, because this is a picture of the beginning of the universe, it tells us a lot about how it got created and what the universe is made of. It's basically a fingerprint of our universe. And this is why science agencies send up 3 satellites to measure this radiation much more finely. So the first mission was COBE in 1989. And so basically, these 3 instruments, they are very fine thermometers. They can measure very slight temperature differences in 1 part in 10,000 in different directions. So COBE went up, and they saw this 360-degree panoramic view of the sky. They saw that there are some cooler spots in some directions, so not perfect 2.7 Kelvin, but slightly cooler. And then there are some hotter spots here at the galactic disk and also away from it. So this was so great that we measured these slight temperature differences that COBE got a Nobel Prize. And there was another mission sent up by NASA, which is called WMAP. And you can see that it could measure these temperature differences much more finely. It has a much better resolution. And then there was a European mission called Planck, which was even more fine, had a much better instrument on board and could measure really all the differences very well. So if we zoom in here, then COBE would see a structure like this. With WMAP, you can already resolve a bit more of the structure. You see some cool spots, you see some hot spots here. And Planck, yeah, you see it's even better, it's even more resolved here. Cool spots, hot spots. Now, why is this important? Well, it's important because it tells us something about the beginning of the universe, and it tells us that there's this substance called dark matter and also dark energy. So how do we infer this? Well, to know this, we have to compare real data to simulations. We have a hunch about how the universe works during the Big Bang, so we can do computer simulations of this early universe, and then we can compare the outcome of these simulations to the real data and see if they match. So for example, if we do a simulation and we put in all the visible matter, that means protons, neutrons, electrons, then the CMB, the cosmic microwave background here, would look like this. So this looks completely different from what you see here. You see many more of these hot spots. You see many more of these cool spots, and they're more extreme as well. And the structure here looks much more smooth than in this scenario where you only have visible matter. However, if we put in, for example, this dark matter, which means some slowly moving particles which can only interact gravitationally and cannot emit any light, then we can make these simulations agree with the real data. So here you see, yeah, same amount of hot spots and cool spots, and the structure looks very similar. Now, you can't compare these two pictures point by point because there's some random initial condition that we don't know. So the only thing you can compare is really the structure, which looks very similar. Now, if you like these kind of pictures and you want to play around with different universes, I encourage you to go to this website after this, and you can play around a bit and see how different universes would look like. Okay, so from this agreement here, we can infer that there's only 5% of visible matter in the universe. There's 26% of dark matter, so these slowly moving particles only interacting gravitationally. And then there's this mysterious component, which I'm not going to talk about much, dark energy, which is 69%. And dark energy is some energy in space, which just fills space, and it tries to force the universe apart. It tries to accelerate the universe. Now, these components here, especially dark matter, they just don't. There's no theorists just thinking, okay, let's add this kind of substance. We actually have indication that this dark matter exists, and we have had that indication for 100 years now. And the reason is that we've measured the velocity of objects flying around galaxies, and the observations don't match our expectations. Let me tell you what the expectations are here. So what you see here is some galaxy here in the middle, and we want to follow these three objects here, which are going to fly around it. Now, the velocity with which these objects fly around the galactic center will depend on its mass, but also inversely on the distance. So these objects will fly like this, and velocity is determined by the mass inside their orbits divided by the distance here. All right, so now we can compare this to the observation. And the observation, that will be the white dots here. And, well, they are much faster than what we expected. Here in the inner orbit, this is pink, so it means these two seem to agree. But the further you go outside, the larger the discrepancy becomes between the expected and observed rotation curves. And the reason for this is, so we believe now, that there is dark matter in our galaxy which extends all the way, and that increases the mass that is there. And it's larger than the mass you can infer from just looking at how many stars there are inside this galaxy. So there seems to be this dark matter component accelerating objects outside in our galaxy. Okay, great. So now coming back to a gallon of space, can we now say how much dark matter there is? Unfortunately not. We have a problem that we don't know what this dark matter is, so only then I can tell you how much dark matter there will be in the gallon of space. Now that might seem disappointing to you, but if you now ask your local particle physicist about this, they'd be really happy to assist you with this question. And the reason is that particle physicists always try to push the boundary of our understanding of nature. They have a huge list with candidates for how to extend nature, and dark matter is an opportunity for them to see if their ideas somehow fit with nature and with dark matter, for example. But it's not that simple. Not every idea just fits. There is a long list of properties that your candidate for dark matter must fulfill. So one thing, it has to be a slowly moving particle. It has to be dark, where dark means that it cannot emit any light. And it also means they cannot interact in any other way too strongly. It's really elusive. It goes through matter easily, and you can't touch it. It has to be there during the Big Bang. Otherwise, the picture of the cosmic microwave background wouldn't work out as it does right now. It has to be there to influence the structure during that period. But it also has to be here today, which means that it has to be stable. It cannot decay. And then it has to give us the correct rotation curves. Okay, there's still a long list which remains after crossing out all the examples that don't work. And I'm just going to present a couple of them, but the best one is over here. But I'm going to start with the WIMP. So the WIMP used to be the prime candidate for dark matter. If you ask particle physicists about the WIMP, they will say, well, for the last 30 years, I would say, they would say, yeah, the WIMP is a dark matter, and it's the most interesting candidate. And the reason for this is that it was really easy to explain how the WIMP came to be in the early universe, how it was produced. And also, it was kind of a beautiful idea because it was a rather heavy particle. So in the particle world, it would be something like a bowling ball flying around in space. And it has a mass which is larger than the proton's mass. So if the WIMP was dark matter, there would be around 1,200 of these per gallon of space. Because the WIMP was so attractive to many physicists, there are currently lots of experiments trying to search for the WIMP. Unfortunately, so far, none of these experiments have found a positive indication for the WIMP to exist. And this is why in the last 10 years, there has been a paradigm shift, a bit away from the WIMP and towards other ideas that might explain dark matter. One of them is, for example, the Macho. The Macho, that's a massive compact halo object. What it means is that it's basically black holes which were created in the early universe, and they fly around in our galaxy today as well. Now, because black holes are rather massive object, that means that if you bought a gallon of space, you probably wouldn't find any black hole in there. And if a black hole made it into this gallon, well, you wouldn't be able to buy it because it had been swallowed by a black hole. Another candidate is the sterile neutrino. So you might have heard of the three visible neutrinos, these three brothers here. We know of their existence, and they like to play with each other a lot. But we think that there's a fourth brother, and this is this one. And it doesn't really like to talk to any of his brothers. So this is why it's called sterile. It takes distance. And because it doesn't want to talk to his brothers or anything, actually, it's a good dark matter candidate. And there would be roughly 10 million of these sterile neutrinos in each gallon of space. My favorite candidate is the axion. And the reason for this is that the axion solves another problem with nature, the so-called strong CP problem, but I'm going to call it neutron's electric spin problem here. And I'm going to explain you what this problem is and how the axion solves it, and hopefully after that you like the axion as much as I do. So the neutron here, so we have protons and neutrons, they make up matter. The neutron has a property called a magnetic spin. So this is similar again to this magnet here I showed you before with the hydrogen atom. And this magnetic spin is such that if you put this neutron inside the magnetic field, that means that the spin starts to rotate. So this is our expectation. The spin rotates around its axis. And this is also what we observe. So this is great. This works. However, the neutron is also supposed to have an electric spin. That is similar, but this one tries to rotate inside of an electric field. So now if you put the neutron inside the electric field, the following happens. We would expect it to spin, but unfortunately it doesn't. So this doesn't work, and this is a puzzle, and this puzzle is the neutron's electric spin problem. Now it turns out that this electric spin depends on the fundamental constant of nature called theta. Other constants of nature you might know are, for example, the electric charge or the gravitational constant. Now this particular constant here seems to be almost zero, very close to zero, because we do not observe this electric spin here. And that's somewhat puzzling. It somewhat means that we live in a very special universe. Let me show you why. So we know that theta lies in between minus pi and pi. And any value on this axis would give us an observable electric spin everywhere except for a very tiny region around zero. And by tiny, I mean 1 in 10 billion. So the puzzle is why nature somehow chose to lie somewhere in this very tiny region. Or put in a different way, if I ask you to give me a random number between minus pi and pi, the probability that you gave me a number where we would observe an electric spin is almost 1. And the probability that you gave me a number which is in this small area here would be vanishingly small. Or in a different picture, let's say we drop marbles on this and just read out the value where the marble falls. We just drop marbles randomly. They might fall here, they might fall there, but the probability that they fall exactly in this very, very tiny region here is very, very small. And we physicists, we're somehow trained to see these odd features in nature because they might tell us something more about nature. There might be a reason why this is. And one reason for this was found by Roberto Pache and Helen Quinn in 1977 when they were both at Stanford. And Helen Quinn later went on to be a staff scientist here at SLAC as well. And they wrote this paper, which was very influential and still is, and they found a method how to get the right value of this theta parameter in the following way. So they noticed that actually this line here is not straight like this. It's actually more bent, more like a bathtub. So now if you drop a marble, it falls somewhere, but it doesn't roll down because the friction is really high, so it wants to stay here. So Pache and Quinn, they envisioned that there is some substance, some oil in the universe, which overcomes this friction and lets this marble roll down to zero. So that means that wherever the marble falls, it will roll down to zero, so the probability that there's no electric spin is actually 1. So that means theta today will be 0. That will remove this electric spin. And this means our expectation now is that the neutron does not rotate inside an electric field, and that matches with the observation. So that's great. Now the substance itself, this oil, is really hard to detect. But fortunately, shortly after this, Frank Wilczek and Steven Weinberg, who was at SLAC for a while as well, starting to think about this, they at the same time but independently found that there's another observable consequence. And this observable consequence of this Pache-Quay solution to the neutron spin problem, this consequence is the axion. And they called it the axion after a famous laundry detergent because the axion removes a stain from our understanding of nature. Okay, so what is the axion? How does it come into this game? Now, if you look at the sea, if you have water, then you know that if you shake it up a lot or you have lots of wind, then you get a wave like this. The axion is the wave of this system here. So if you shake up this bathtub here, it will form a wave. It will get excited, and this excitation is the axion. Now, it turns out the axion is a good dark matter candidate. It ticks all the boxes. It doesn't interact very strongly. It gets produced during the early universe. So it is a dark matter candidate, but it's an unusual dark matter candidate. And as Michael said in the beginning, it's especially unusual because it's very light. So if this is the Whim, then the Whim will be much heavier than the axion. And to be more precise, if the Whim was as heavy as a tanker, then the axion would have the mass of an eyelash. It's really, really small. And the axion has another interesting property. It makes a ghost-like appearance in the early universe. While Whims get created during collisions of standard particles that we know of, so neutrons, electrons, protons, collisions like this, the axion just appears out of nowhere. It just comes to be. And the reason for this is that in the early universe, this oil got created at some point, and when this oil got created, the axion came to life. Okay, great. So now that we've heard that the axion can be dark matter, we can finally say how many of these axions you would find in your gallon of space, and it turns out it's 10 to the 19. Now that number doesn't, or might not tell you very much, but this is the amount of insects you have on Earth. So in each gallon of space, you would find as many axions as you have insects on Earth. So if there are so many of these axions flying around, why haven't we seen them? It turns out axions are really hard to detect. They just fly through brick walls without caring about it. And that's a problem because our detectors, for Whims, for example, they rely on the fact that when dark matter particles fly through them, these dark matter particles collide with our detector and leave some trace. Axions don't do that. And the problem is even worse. Even if our whole visible universe was made out of brick, the axion would just fly through it without caring much. And this is why this axion was called the invisible axion for a while. Now, luckily, there is a different way. And here I have to credit Pierre Sikivi, who's a professor in Florida right now, and he was a postdoc here at SLAC for a while as well. And he came up with ideas how to actually detect this seemingly invisible axion. Now, the detection technique relies on the fact that an axion and a photon, so electromagnetic wave packet, are actually the same thing when they travel inside a magnetic field. So that means that if you have an axion here, you can convert it into a photon if you apply a magnetic field. And the probability for this to happen, which I would call G gamma A, is this parameter G gamma A. Now, if you have trouble understanding this, imagine a coffee machine. A coffee machine converts water into coffee. So the water will be the axion, the coffee is the photon, and then you have to put some beans on the top, which will be the magnetic field. But this coffee machine is special. It works in two directions. There's the standard coffee machine, which converts axions into photons, but there's also an inverse coffee machine. And this one filters out the coffee. It converts a photon into an axion. So this works both ways. Okay, great. So now we have a method how to try to detect the axion. Let's look at a map on what we have to do. So this is the parameter space of the axion. You have a mass here. This is 1 electron volt, which corresponds to 1/1,000,000th of the mass of the electron. And you go orders of magnitude down here. Here on this axis, you have the probability to convert an axion into a photon or in the other way. And up here, the axion is basically like chewing gum. If you throw it against the wall, it just sticks to it. Down here, it is really like a ghost. It just goes through everything. It's really, really hard to detect. Now this blue region here, this is where we want to get, because this is where it's easiest to have the axion and to have it solve both the neutron spin problem, neutron's electric spin problem, and also the dark matter problem. So this is where we try to get. But that doesn't mean that all the other white areas here are uninteresting, because the axion could also live somewhere here, but that would mean that we would require some more work to understand why the axion would be in these areas. Or it might mean that the axion is not dark matter and something else, or it does not solve the neutron's electric spin problem. It's a bit more complicated if we're somewhere here. Okay, so the most advanced experiment is the axion dark matter experiment, ADMX. And this one got started at Livermore Lab and is now being performed in Washington University. And they rely on an electromagnetic cavity like this. So a cavity, that is an instrument which is very sensitive to a particular frequency of the electromagnetic spectrum, and only to that frequency. And this cavity they put inside of this rack, and you have very strong magnets inside here, and you cool it down very close to the absolute zero of temperature. And then you wait and try to see the axion. So what you hope for is that some of this dark matter axion just flies inside your cavity and then gets converted into a photon, into electromagnetic power that you can pick up. So this is basically just a coffee machine. You wait for the axion to come in, and you try to get the coffee out. Now, because the cavity is very sensitive to a very particular frequency, it means that it's very sensitive to a particular axion mass. So what you have to do, if you want to scan all this parameter space, you want to know if the axion lives at that mass or at that mass, you have to tune your cavity to different masses. And for this, there are these rods inside here. So when you turn them, the following happens. The field in your cavity changes, so the rods are here. And at the same time, the frequency that your cavity is sensitive to changes as well. Now, this is not as fast as shown here, so usually it takes a couple of months or a year to scan through all this. And while you scan through this, what you try to look for is a peak like this. So usually you have just some random noise, but what you try to see is that there are actually some axions flying through it, and then you see this additional power and a peak. And from the position of this peak from the frequency, you can infer what the mass of the axion actually is. But if you do not see a peak like this, you can also say that there's no mass, no axion living at that particular mass. So ADMX has searched for the axion. So far it hasn't found it, but it can tell us already that the axion cannot live in any of these gray areas. So this is not only ADMX, there are also other experiments which are similar, which also give us bounds like this. Now, because in the last 10 years, the axion has gotten more and more track, and there are more theorists are thinking about it, there were lots of proposals on how to detect it, also in the other regions here, which are currently not being probed. I just want to mention two of them which are somehow dear to me. One is the dark matter radio. This is an experiment being done here at Stanford and at SLAC. At the moment, they're doing R&D to go for very low mass axions. The other one is MatMax. And the reason I like MatMax so much is because my former supervisor, Javier Redondo, actually came up with the idea. And last October, they formally started the collaboration and do R&D to finally detect the axion. And, well, Javier is also the one who basically brought me into axion physics and made me work on this. That's pretty cool. So with these ideas, in the future, we will be able to test all this red area here. This is what we will be able to do. Unfortunately, these experiments have the assumption that there's actually axion dark matter flying around. So that means they assume that our galaxy is filled with these axions, and there are also some of them in our solar system, and they just fly into our cavity and get converted into photons, and we can pick them up. However, it might be that the axion doesn't look like this, but more looks like has a clustered structure. So there might be some axions flying around here, some here, but there are none right now in our solar system. And that will be a problem with these kinds of searches, because then there are no axions around to detect. So this wouldn't work. So there are other ideas how to then detect the axion, but they're a bit harder because you have to first create an axion and then measure it. But a cool idea is the so-called light shining through the wall experiments. So what these experiments do is they take a laser and they point it against the wall. And then they put a detector behind the wall. So if there's no axion, what you would expect is that your laser shoots a photon, it gets absorbed by the wall, you don't see anything behind the wall. However, if there is an axion, we can do the following thing. We put a magnetic field before and after the wall. And so the left-hand side here, that's the inverse coffee machine, so it can create an axion. And the other side is the normal coffee machine creating a photon. That means we send the photon, it gets converted to an axion inside the magnetic field. The axion just goes through the wall, then it gets converted back into a photon, which we then can pick up. So suddenly you have photons where there shouldn't be any, and that's a smoking gun signal for this axion to exist, independent of if it's dark matter or flying around in our solar system or not. So this kind of experiment is currently being performed in Hamburg at DESY in Germany. And they use a laser. They have a cavity, a laser resonator here with lots of magnets around. So for 100 meters in front of the wall and 100 meters behind the wall. And these experiments are rather cheap because they also reuse lots of equipment from other experiments we have done before. So they use dipole magnets from the Hera experiment. Hera was a particle collider which ran in the 90s, and they just reused those magnets to do this kind of experiment. And they are currently looking for the axion, and they will be able to probe this area here. Now this is actually stunning because I told you it's really hard to do these experiments because you first have to create the axion, which is hard. And then you have to convert it back into a photon to detect it, which is hard again. So it's really impressive that they can reach so far down. And okay, they might not be able to reach this favored region here in blue, but still, it would be interesting to see if there is something here, and if we found something, it would definitely be really, really interesting. So we can take this technique and ramp it up. So instead of a laser, now we're going to use the sun. The sun emits photons and convert these photons into axions. The axions then fly towards Earth, where we wait with a magnet here and some X-ray detectors, and the wall is this shielding here in front of the magnet. So with this, you look at the sun for a couple of hours a day and try to see if there are some photons somewhere where you don't expect any. And this is being done by CAST at CERN at the moment. So this is an LHC prototype magnet here. They ramped it on a rack, and with this, they follow the sun for a couple of hours a couple of hours a day, and try to see if there is an axion. Now, there's a ramped-up version of this, which is currently being developed, which is IXO, the International Axion Observatory. And yeah, this will be much better than this than the CAST. Okay, so this is what the light shining through the wall experiment could do, the ALPS. So with CAST, we are able to probe this. So CAST was able to exclude the existence of an axion in this gray area here. So they even reached down to the blue region. And IAXA will be able to reach even further down and further into this favored blue region here. Okay, now we use the sun, so why shouldn't we use black holes and blazars? So the blazar is a black hole accreting matter converting into this very intense radiation, and these photons might reach Earth as well, where we are waiting with our Fermi satellite, and we have lots of scientists here at SLAC as well working on Fermi and trying to, for example, measure the photons coming from these blazars. Now, where's the wall in this game? As I told you before, there's these cosmic microwave background photons flying around in space. And it turns out that these photons are somewhat a wall to these very high energy photons, gamma rays, coming from the blazar. But there's a very good video from NASA, which I will show you now, which explains this much better. So this was the blazar, and it emits this high energy particles. And here you see the high energy photons. And they're flying in a straight line. And shortly after here, you see these blue photons coming in. And those are the CMB photons. And they just fly randomly around. And sometimes it might happen that these photons hit one of these high energy photons, and they create an electron-positron pair. And these electrons and positrons, they could just go in some other direction, so you can't see them later. Now, not all of the photons will be absorbed. Some of them will make it to our galaxy. And some of them will also make it to our solar system, so you see the sun here. And there's the Earth, and we have the Fermi satellite waiting for those photons. There it is. So when these photons come in, they again create an electron and a positron, which we can then measure so that we can say we detected a photon. Okay, so we have a wall, but the wall is kind of leaky. Not every photon gets absorbed. Some of them make it through. So, but with this leaky wall, we can still do a light shining through the wall experiment here. So we know that there is a magnetic field in space. So what we can do is, there's a photon coming from this blazar. It gets converted into an axion. The axion just flies through the cosmic microwave background without caring much about it. It gets converted back, and we can pick it up with Fermi. So because the wall is leaky, measuring these photons does not necessarily mean that there is an axion. So here what we have to do, we have to compare our predictions for how leaky the wall is with what we measure. And from this we can infer that maybe there is, we see many more photons than we expect, and that would mean that there is something like an axion, decreasing the absorption of this wall, the leakiness of this wall. Okay, so this is what we could do before. And with this method, we are able to exclude this area here. And this is what we might be able to do in the future. And this is actually a result I wrote a paper about a couple of months ago. So very proud to present it here. So with all of these searches and also dark matter searches, we will be able to probe all of this at the moment. Okay, so what if we found it? What if ADMX suddenly saw a peak like this in their spectrum, something like this, and they can say with confidence, oh, we found the axion, it's dark matter, it has this and this mass. Well, first of all, this would be a revolution for fundamental physics, and we then understand why there is no electric spin of the neutron. It might tell us what dark matter is, finally. And it also has implications for high energy physics. And the reason is that the mere existence of the axion tells us that there is this oil substance I was talking about before. There was this oil which made the marble roll down. And this might motivate more searches for this oil at high energies, at colliders, for example. But there's also more fun stuff you can do with an axion, but beware, what I'm going to say now is rather speculative. There's no guarantee that this will work ever. But what you can do is you can use the axion as a communication channel. So, for example, you're standing on one side of Earth and you want to communicate with your friend who's on the other side. What you usually have to do, you have to send a photon around Earth. With the axion, you can send a message right through Earth. And that's much better. You're 50% faster in communicating. You can also use it to do physical encryption. So let's say you're here, you have you want to deliver a message to your friend who's on a spaceship, somewhere in orbit, for example. But there might be somebody sitting in between trying to read your messages. And if you send a photon, well, then they might pick it up and try to read what you were saying. With the axions, it might be a bit harder because if you send the axion, then you have to know at what frequency the axion was sent to be able to really measure it. And the reason is that it takes a lot of time to scan all the different frequencies to finally find a peak like this. That means if you tell your friend before you left Earth that I'm going to send my messages at this particular frequency, then he or she will be able to tune their axion detector exactly to that frequency, and it will be rather easy for them to detect your message. Somebody else who does not know at what frequency you sent your message, well, he has to scan through all of this to actually find that you were communicating. Okay, even more speculative is axion space travel. So if you're in your spaceship and you have all these axion dark matter flying around, then you might as well use it, right? So, for example, if you had a cavity like this, then you might hope that some of these axions enter your spaceship, enter your cavity, get converted into a photon, and you can pick up this energy from the axion and use it to power your light bulbs or whatever you need in a spaceship. You can also do axion sailing. So there's a flux of axions coming in, you convert them into a photon, they bounce off a mirror and give a thrust to your spaceship. So that now you have a way how to do sailing on this axion wind. All right, so we've come a long way from this picture of the night sky where we talked about stars and about how empty space really is. You've learned that there's hydrogen, that there are photons inside there as well, and that there's also dark matter. And this dark matter, well, that might be axions. So the next time you go outside and look into the sky, I hope that you do not only see this, but you might actually see the ghost riders in the sky. Thank you.
We have time for some questions. For those of you who haven't been here before, the process is the following. You all have these microphones in front of you. In the center at the bottom, there's a red button. Only one person can have their microphone on at a time. So get recognized. When you're recognized, press the red button. Then you can be heard. And then when you're done, turn off your microphone and the next person can have a question. So who'd like to ask a question? Please.
So your helioscope and other detector methods, the Earth has a magnetic field. So what do you do about that?
Say again.
The Earth itself has a magnetic field.
Yes.
You're expecting the axion to pass through a magnetic field and be converted to a photon at I think in the 100 megahertz area. But the Earth has a magnetic field, so.
Right. You can estimate how big the conversion rate is of axions in the magnetic field of the Earth, and it's not that large. The magnets are much more powerful, orders of magnitude, and this magnitude of the magnetic field is what dominates the conversion probability.
So the magnets in these experiments are what, 6 orders of magnitude, a factor of a million?
Yeah, something like that. Yeah.
Who's next? Please.
The SLAC magazine Symmetry announced that there was a galaxy found, a diffuse galaxy that has virtually no dark matter in it. Does that affect, how does that fit into the notion of the axion?
Yeah, I haven't read the paper yet. I guess it's rather puzzling that there's no dark matter. But in this case, it might be that there are certain patches in the sky or certain regions where there is no axion dark matter, for example. So if you think about axions, it might be that there are certain areas where there's more and where there's less of it. So it might be that these galaxies form without dark matter. But yeah, I haven't thought deeply about the paper yet.
Do you think that at the time of recombination, or before the time of recombination, 380,000 years after the Big Bang, these axions were contained within the volume, or had they escaped already?
Well, so recombination, that means that's the point in time when the Big Bang happened and the photons were emitted. And so you're saying that these axions just fly?
Well, until that time, the microwave background was captive.
Yes.
Okay? Now, what I'm asking is can you imagine whether the axions were also captive?
So the axions are so ghost-like that they would not be captured like the photon.
No.
They would just be there as a background.
Inside or everywhere?
Everywhere. It depends a bit. Some people would say there might be certain areas where there's less dark matter, so less axions, others there's a bit more. But in general, they would just be there at that time. And on average, you have to get the right amount of dark matter in your universe. But it might vary from area to area.
Sir.
Did you say during the lecture that the axion was 1/1,000,000th the mass of the electron?
That's about the maximum in the mass scale which it can currently have, yes.
So that would make the axion then even more ethereal than the neutrino.
So you say less massive than a neutrino?
No, the mass of the neutrino I've heard quoted as being about 1,000th the mass of an electron.
Yes, right. So, I mean, there are 3 of them, 3 of these neutrinos. One might still have a mass of 0, which we don't know. But one will have a mass of 1,000th of an electron volt. But the axion can be anywhere in that range. It can be heavier than this neutrino. It can be lighter than that one.
I see, okay. Thank you.
If they're that light, then at the time they formed, they'd be hot and relativistic. And if they're relativistic and no way to slow down, then how would they clump around matter? Because that's normally why you want a Whim, a weakly interactive massive particle, because, in order for it to clump, if you don't have a way to radiate, you can't clump. How does that work?
So that's the fun thing about the axion. Although it's so light, it does not create it like the Whim. It does not get in thermal contact, or it does not get heated like the Whim does. When it gets created, it's in its lowest energy possible. And that means it's really, really slow when it gets created. It moves, well, for our standards, there's still a large velocity, but for particle standards, a really low velocity. So it is cold dark matter. It is cold when it gets created, and it stays so.
It has to be in thermal contact with the thing that creates it.
Now, the reason, well, it gets created not through these collisions, so it's not going to get in thermal contact. It gets created because this oil gets created in the early universe. There's a phase transition where we suddenly are in a vacuum where you have this oil, and then you have very slight excitations of this oil. That's the axion. Just because, well, you can also think of it in the following way. When your model falls down on a certain value, then when the oil comes into existence, the model rolls down and starts oscillating around 0. It actually doesn't stop at 0. It starts like moving like this. But this is a very slow rotation, this oscillation, this very slow oscillation, that's the axion. And this is not getting produced from anywhere, but really low energy oscillations. It's complicated, I know. We can talk about it later as well if you want.
Let's take 2 more questions. First one is you. Please.
What do you think about the possibility that dark matter consists of more than one type of particle?
That might very well be.
Anyone else?
Okay. Yeah. In your theories of dark matter, or particularly with axions, would you predict a single type of particle, or are you thinking that maybe a whole family of axions could possibly exist?
So, yeah, that's a good question. So, what you want is at least one axion to solve the neutron's electric spin problem. But there are a couple of theories which predict a whole family of these. And actually, the white space I was showing you before on this map with a favored region, the white space would be probably more filled with these family of axions instead of the axion itself. Now, you might debate about if these families really exist, but there's some theories like string theory which would predict that there's these kind of axions and a whole family of them.
Okay, well, let's thank Hendrik very much. Okay.